Okay. Thank you for the introduction, and thanks everyone for coming. I'm Yuepeng Wang from UT Austin. I will be talking about synthesizing database programs for schema refactoring. And this is joint work with James Stone, Rushi Shah, and Isho Dilik. Database-driven applications have been super popular for web development. Most contemporary websites are built using database-driven applications in order to generate the web page content dynamically. During the evolution process of these database applications, schema refactoring is quite common for performance or maintainability reasons. There are two things that we need to do after the schema refactoring. First, we need to migrate the data from source schema to target schema. And second, we have to re-implement parts of the program that interact with the database. So this typically involves significant changes to the existing SQL code. Among these two aspects, the data migration part has attracted lots of attention from researchers. However, the code migration problem did not gain that much attention, and therefore is mostly done manually. As you can imagine, migrating database program is not an easy task. It would be super exhausting if you update the functions manually, and it's very easy to introduce bugs during this process. Equivalent to the source program. Let's look at a concrete example. Suppose we have two tables in the original database, the instructor and the TA. The instructor table has three columns, the instructor ID, the instructor name, and the instructor picture. Similarly, the TA table also has three columns, the TA ID, TA name, and the TA picture. And later, the developer decided to put the pictures into a separate table, so they refactor the database and get this new schema. Now, there are three tables in this new database. The original instructor and TA pictures are now stored in this new picture table, and the correspondence is built using foreign keys. Then let's look at the program that we need to change. In this talk, we will assume the database program is a set of update or query functions, where the function bodies are parameterized SQL statements. So for instance, in this sample program, we have three functions, one for adding a TA, one for deleting a TA, and one for getting the TA information. After the schema is changed, all these three functions need to be re-implemented to make sure the new program is equivalent to the version before refactoring. For example, for the add TA function, the original program simply inserts the ID, name, and picture into the TA table, but the target program needs to have two different insert statements to put the name and picture into different tables. Similarly, the new deletion function also needs to delete the TA information we need to enumerate all possible value correspondence in the worst case and in decreasing order of likelihood. However, first computing all the value correspondence and then sorting them is not a good idea, because the number of value correspondence would explode as we get more columns in the schema. To solve this problem, we perform a lazy enumeration using maxset to generate a next likely value correspondence on demand. Here, the maxset is the optimization version of Boolean satisfiability, where the constraints are divided into two parts, the hard constraints and the soft constraints. And the goal of maxset is to find an assignment of all the Boolean variables such that all the hard constraints and the maximum number of soft constraints are satisfied. In our context, we use hard constraints like type compatibility to enforce the generated value correspondence is valid. And soft constraints, such as prefer mappings with similar column names, would enforce the optimal solution of maxset is more likely to be an intended one. So if the value correspondence is not what we want, we can simply add a hard constraint to block the current model and move on to the next one. So this allows us to enumerate all the value correspondence in the lazy way. Although a value correspondence can dramatically constrain the search space, it actually cannot uniquely determine the target program. So based on this observation, we use a program sketch to represent all the programs that may be equivalent. Going back to our running example, so given this candidate value correspondence and the function in the source program, we would generate the following sketch. So here, a sketch is very similar to a normal database program, but the only difference is that it has one additional construct, this question mark. The question mark here denotes a hole in the sketch, which means some join structure or table name or column name is unknown. Then with the help of the value correspondence, we can determine all the possible instantiations of the holes. So for example, this one says that this hole can only be instantiated with picture join TA or picture join TA join instructor. So after the sketch generation, the final step is to solve the sketch. One natural solution is to enumerate the sketch completions by enumerating all the candidates for all the holes. And then for each completion, we check if the obtained program is equivalent to the source program or not. Unfortunately, this simple solution doesn't work well in practice because of the scalability issue. Well, suppose you have a very simple sketch that has 15 holes, and each hole has 3 instantiations. Then you will have over 14 million completions to explore in total. To address this scalability issue, we introduce minimum filling inputs to prune the search space. So here, a minimum filling input is the shortest sequence of function invocations that can differentiate two database programs. So for our example, suppose this is the candidate target program that we get during the enumeration, but it's actually not equivalent to the source program. We can use this input to differentiate these two programs. This input basically says that we first add a TA to the system, and then we query the information of that particular TA. Executing these two functions on this candidate program would produce different results from executing them on the source program. Specifically, the source program will produce the correct TA information, the name one and picture one. But this candidate target program will just give you empty result. Furthermore, this invocation sequence is one of the shortest because it only has one update and one query. So this is the minimum filling input. To see how this is useful for pruning the search space, let's consider a source program P, an incorrect target program P prime, and a minimum filling input MFI to differentiate them. Our key insight here is that any program under the target schema that agrees with P prime on those functions in this minimum fitting input will also be incorrect, because it will produce exactly the same wrong result as P prime on this input. So based on this insight, we can prune multiple incorrect programs in one iteration, rather than just prune a single program that we have encountered. All right, incorporating this pruning technique into the enumeration, we get our sketch completion algorithm like this. Given a program sketch, we first encode all its possible completions as a set formula, such that each satisfying assignment of the formula corresponds to a completion of the sketch. Then we check if this formula is satisfiable or not. If it's unset, we can directly conclude we cannot complete this sketch. If it's satisfiable, we ask a model from the set solver and then get a candidate target program. Next, we check if this candidate program is equivalent to the source program. If they are equivalent, that means we have found a correct completion of the sketch. Otherwise, we ask for a minimum fitting input from the verifier as the witness of this equivalence. And then, based on this minimum fitting input, we generate a blocking clause to prune the search space. So we repeat this procedure until we find the correct completion of the sketch or the formula is no longer satisfiable. So far, I have been talking about the techniques for automatically generating the new database program. Next, let's look at the experimental evaluation. So in order to evaluate the effectiveness and efficiency of our proposed technique, we build a research prototype called Migrator and use it to synthesize 20 benchmarks. These 20 benchmarks are collected from prior work, where half of them are from textbook and online tutorials, and the other half are from Ruby on Rails applications on GitHub. Each of the textbook benchmark here has about 2 tables, 8 columns, and 10 functions on average. And the GitHub benchmarks are much larger. They normally have over 10 tables, 100 columns, and has about 105 functions on average. Migrator can successfully synthesize all of these 20 benchmarks, and is also quite efficient. As we can see from the table, for the textbook benchmark, it only enumerates 3 programs to find the correct one, and the total running time, including synthesis and verification, is about 6 seconds on average, where the synthesis part only uses less than 1 second. For the GitHub benchmark, the takeaway message is that Migrator can synthesize database programs with over 100 functions in 2.5 minutes. Okay, to wrap up, in this talk, we have proposed a novel synthesis technique for automatically migrating database programs to a new schema. And we built a research prototype called Migrator and evaluated on 20 benchmarks from textbook and GitHub. Our evaluation results shows that Migrator can synthesize new version of database programs with over 100 functions in a matter of minutes. With that, I'm happy to answer questions.
Is it working? Oh, it's working.
Great talk. Thank you. So the question that I had is that the input language to Migrator seems to be restricted with respect to, let's say Ruby on Rails, in which the apps are actually written. For example, it doesn't support, I guess, dynamic control flow for queries. So, and yet you're saying that you were able to actually use Migrator to migrate all the apps that you found on GitHub. Is it that the apps on GitHub are just like, written in Ruby on Rails are all really simple and they don't use these advanced features? Or what's going on here?
Okay, so there are 2 parts of the question. So first of all, Migrator does not support the control flow. You cannot use control flow in our input language. But the second part is that it's not only about Ruby on Rails. It's more general than that. So the technique can be applied to any database programs that using SQL. So you can first extract this kind of database part from the Ruby on Rails applications or some Java applications or Python applications, and it can work on that.
Right, but those applications might be generating queries, for example, dynamic.
Right, we don't support the dynamic
Right.
generated queries.
Okay, but are you
All
saying
the
that
queries
most,
are
yeah,
like
most
static.
applications on GitHub do not have those advanced things in them, like dynamic query generation? That's why you were able to convert them all to the input language of Migrator.
Maybe, yeah, but yeah, like all the functions needs to be statically known. Yeah.
First of all, thanks for the talk. It was great. I was wondering why we generate, or you generate, a value correlation when we have a migration most of the time, which would in theory express the same thing.
You mean the value correspondence?
Yeah, oh, sorry, yes, value correspondence.
Okay, so the value correspondence basically states which source column maps to which target column. So this can dramatically constrain the search space, as I said. I mean, and then if the value correspondence is wrong, we can enumerate to the next. We can go on to the next one. So this gives us some way to enumerate the search space efficiently.
Yes, but presumably for these applications, we have the actual like schema migration in SQL, right? Like, so why not just extract it from that? Why generate it?
I see. Sure. Yeah. If you have the migration script, we can definitely get this value correspondence from that. But here, our input is only the source schema, source program, and the target schema. We don't assume you have this migration script. But definitely, if you have that, you can generate the value correspondence from the script. Yeah.
Thanks.
So for applications that need to be highly available that can't have downtime, oftentimes developers will do a staged migration in some way where they actually support, running a new query and an old query on different web servers at the same time using some common database schema as an intermediary. Have you thought about whether your technique could be used for this situation as well?
Yeah, but we currently don't support that. So as you know, the synthesis time is I think to me is quick enough, is good enough. There will be some downtime, but it's not very long. But you are right. We can, even if you want to generate like two different versions of program, that one version interacts with the original database, the new version interacts with the new database, we can still use our tool to generate the new version, right? But you just need to run these two versions somehow together. But that would be an interesting future work, I think. Yeah. Okay, let's thank our speaker.